Hi, everyone. So, I wanted to get started by talking a little bit about the plans for this week. So, we are going to be hosting a couple of tutoring sessions. I'm going to post all of this information on Google Classroom for you to have access to it. But we're going to be doing some Zoom sessions with Mrs. Petruzziello's and Mrs. Guerra's classes tomorrow as well as Wednesday. And that's all to prep us for a little test that we're going to have on Thursday. Now, the test Thursday won't be all of electricity because we haven't learned all of electricity yet. It'll be just up to whatever we've done, including today. And so today I wanted to introduce a new concept, and I want to talk a little bit about electric potential difference, what that is, and how we can calculate it. So, what do we know will happen if two positive charges are near each other? So we know that if we have two positive charges, those are like charges, and we know that like charges will repel. But we can still make them come close together. That's just going to require exponentially more force as they get closer together. Distance changes. So the really clear real life example of this would be to think about almost like a magnet or having two magnets. And I know that a lot of you have put magnets before where we try to bring them together. And bringing them together, it's possible. It requires more force and more force and more force, but you are strong enough to actually bring them together. So obviously that's going to require a little more force, and as we apply that force over that distance that travels, we can think about that as work, as doing work. And this is the same work as when we talked about work in the past, when we talked about like forces and stuff like that. Same idea, same formula, but now instead of applying it to like a force applied, we're applying it to electrostatic force, and we're applying it to all of these particles that are being moved towards each other. So, as we do work on a charge to bring it closer to a repelling charge, the potential energy of the charge, we call it electric potential here, increases. So, back when we talked about energy, we considered work to be done on something that was gaining some potential energy. Same idea here. As we bring those charges closer together, those charges are going to gain some potential energy. Here it's called electric potential just because it refers to electric potential energy. Uh, and we can kind of write down a definition for that. Electric potential is the potential energy of an electric charge. So what I want you to keep in mind here is that a lot of times when they talk about, when on the Regents they'll talk about electric potential, they'll talk about electric potential and work interchangeably. So work is the same as electric potential. Which makes sense because back in the days of learning about potential and kinetic energy, we would say very often that work was equal to potential energy, that it was the same general idea. Now, another way we could think about this, thinking about gaining this electric potential, is thinking about the difference in electric potential when we have a charge moving across a circuit. So we have a circuit here. A charge will be moving across the circuit, going starting at one end of the battery, going to the other end of the battery. And because we did work on this charge, it has more electric potential at the end of its movement when compared to the start of its movement. So let's say that we're trying to get this charge to move. We apply some work, or we do some work on this charge, it's going to get it to move. And we can call this difference the electric potential difference. It's the change in electric potential of a charge as it is moved from a start point to an end point. So difference literally means exactly what you think it means. I had some electric potential at the beginning, I have more electric potential at the end, so that difference is going to be my electric potential difference. Now, why am I building up this electric potential here? Well, the way that batteries flow, and we haven't really talked about this yet, but the way that batteries flow, we know that the current, the electricity that's running through the wires is going to be electrons. And so we've got little electrons running through this wire, little negative charges running through this wire, and they're heading from the positive terminal all the way to the negative terminal. Now, I want you to think about what's happening here. We're starting at the positive side of the battery. As we head closer and closer to the negative, well, we're going to have to do more work. We're going to have to apply more force here because this is requiring more forces due to the fact that they want to repel. They don't want to actually head towards this negative side of the battery. So as it gets closer and closer, it's going to increase that electric potential, that extra potential energy. Okay, so now we can actually calculate out this electric potential difference. And the electric potential difference is also known as voltage. Now, I'm sure you've heard of the word voltage before. We measured it in volts, and volts is just a big V. Work is the same as it's always been. Just keep in mind, again, that work can be used interchangeably with potential energy. It can mean the same thing, and this is measured in joules. Q is charge, which is measured in coulombs. Talked about that a million times. Now, the last thing I wanted to contextualize for you is how this is actually applied in the real world. So in the real world, we'll say something like a 12-volt battery, and that means each charge is actually going to gain 12 joules of potential energy as it moves through the battery. That's the idea when we say 12-volt, 20-volt, etc., etc. It has to do a lot with like how strong a push you're going to give the charge that you are moving across your battery. I'm going to hold on for a second here. If you want to pause the video, you can write this down, take some notes, and you can move forward from there. Okay, so now we come back to this photo, this diagram, I should say. And this diagram I showed you a few days ago, just to kind of get across the idea of what resistance and current were, what the difference is. But now we were able to identify that third factor, that voltage, that electrical potential difference. So current is the charge that's going through the wire. Resistance is something that's slowing that charge down. So resistance, we talked about it, a few different factors that could affect it. I want you to take a second and kind of list them out now. So we know that the factors that affect resistance are the resistivity, so that's like the material that the object is made of, the length, the cross-sectional surface, the cross-sectional area, I should say. All of these factors will affect how much resistance you can provide. And finally, now we're introducing this idea of voltage. And voltage is the push that is forcing the current to go through. So a bigger voltage should, in theory, push harder, and we should be able to go a little faster throughout the circuit. Now I want to do some application of the math. We can go through these one by one just so we all have an idea of what we're supposed to be doing here. So problem number one, if 20 joules of work is used to transfer 20 coulombs of charge through a 20 ohm resistor, the potential difference across the resistor is, okay. So I would say this is probably the most straightforward way that we could be presented this problem. So we know as soon as we see something like 20 joules of work coupled with 20 coulombs of charge. So I'm getting here a work value of 20 joules, a charge, so my Q of 20 coulombs. And I'm told 20 ohm resistor, but it's actually not really relevant because we don't have a formula right now that combines resistance with charge, work, etc. And we're asked for potential difference. Remember, potential difference is going to be that voltage. So we're solving for voltage. We don't know what it is. The formula is V is equal to W over Q. And that's going to be V is equal to 20 over 20 to give me 1 volt. So my answer is number 1. Cool. All right, so let's try number 2 now. How much work is done in moving 5 coulombs of charge against a potential difference of 12 volts? So now we're being given a slightly different information. We're being given 5 coulombs of charge. I know that that's going to be my Q. Potential difference of 12 volts, so my voltage is going to be 12. Now, the only other thing that I have to keep in mind here is that I'm solving for work. I don't know what work is. I'm being asked how much work is done. That's going to be my unknown. So with that in mind, again, my formula is V is equal to W over Q. And that's going to be equal to, or become, 12 is equal to W over 5, which means that my work is equal to 60 joules. Final problem. A 12-volt automobile battery has 8.4 times 10 to the third coulombs of electric charge. So told that it's a 12-volt battery has 8.4 times 10 to the third coulombs of electric charge. So immediately I can see that I'm given an information for voltage, which is 12 volts, and for charge, which is 8.4 times 10 to the third coulombs. Approximately how much electric energy is stored in the battery. So that is asking me for, just so that you keep in mind, remember, electric energy. Here, it's not phrased as work, but we said that potential energy in a lot of these problems is considered to be the exact same thing as work, because the work is causing you to gain potential energy. So as soon as I see electric energy, I know that I'm being cued in. Okay, this is potential energy, and potential energy means the same thing as work. So I am, again, just solving for work. So I can set up my problem. V is equal to Q over W, which means 12 is equal to 8.4. Ooh, sorry. That is not the right area for that, because we're solving for my work. So we're solving for work over 8.4 E3. And when I solve out for my work, I get 100,800 joules. Okay. That should be enough to wrap up any information that you might see on your review that I'm going to post in a little bit as well, and you'll be able to see in Google Classroom. And the review is just meant to be targeted towards getting you ready and confident for your test on Thursday. One more thing I want to talk about before we kind of break off for today, and that is looking a little bit ahead. So I have two circuits here. One is in parallel, one is in series. And I want you to think about how these two different circuits affect two factors that we've talked about in the last few days. The first one we learned about today. How would voltage be affected by a parallel versus a series circuit? Now, your grade for today is going to come from this question, from you filling out these questions. So please take a second and answer this. The second thing I want you to keep in mind, or think about, the second factor I want you to think about is, how would resistance be affected or be different in a parallel versus a series circuit? So how would the resistance feel differently when it's like all resistors in a row versus resistors in different pathways? And that's something I want you to think about. All right, if you have any questions, feel free to text or email me. And just make sure to complete that test review that you can see in your Google Classroom.